Good afternoon, everyone. I see we have 4 students here. I think we're going to increase it by, hope, a great number. Okay, as the students are coming in, I want to just go back a little bit and talk about something just from yesterday. Well, actually Tuesday. I had a student who came to office hours who asked, how did I know how to draw my chart? And that was a good question. So let's talk about that briefly. So remember, we were talking about solving a ordinary differential equation using Euler's method. And so the question was, well, you had the chart already drawn when we were doing the problem. So how do I draw the chart? Okay, so this is how one would draw the chart. So this is the 2 problems that we worked on yesterday. So suppose you have something, I'm just going to come up with any type of problem, which is, let's say, using Euler's method with h equal to 0.5, find y of 3 if, and then the differential equation will be dy dx is equal to, let's just say xy, something simple like that. And I give you y at 1, y at 1 is equal to 1. Okay, so this is the problem. And so how do I even begin to start to solve this problem? Okay, so remember Euler's method, that means we are starting with our initial values. So can somebody tell me just from this problem, what are x naught and y naught? In other words, where are we starting? Anybody want to tell me where's x naught? What is x naught and what is y naught?
Is it x naught 1? And
Okay,
1?
so here we're going to get x naught is indeed 1. All right, so x naught is 1. How did you get that?
I looked at y1 equals 1 and the
Okay.
1 in the parentheses.
All right, so that's what's in the parentheses. All righty, good. So x naught is 1. That's what's in the parentheses. And then y naught is the actual function value. And for this problem, I also made it 1. So it is 1. Okay, so those are the first 2 pieces of information that we start with. All right. Now, the question is, how far or how many iterates do we need? Okay, can anybody kind of get an idea or guess how many iterates that we need?
3.
Okay, so you said 3. And is that because you're asked to find y of 3?
Yeah.
Okay, so 3 is going to be where we want to go to. All right, so we're starting with knowing y when x is 1. What we now want is y when x is 3. Okay, so that means we have an interval . Oh, that should be a 1. An interval from 1 to 3. And here's where we figure out how far we need to go. Okay, so h is our increment. All right. So just like before, when we did the trapezoidal rule and Simpson's rule and the midpoint rule, we had h was equal to b minus a over n. Well, now we're going to solve for n. So n is going to be b minus a over h. So b minus a is 3 minus 1. That's the 2 units that you're looking at here. and the length of each one is 1/2. That's the 0.5. So I get 2 divided by 1/2. So that's 4. So let's see, that makes sense. If I divide it up into 4 intervals, if I add a half, so I'll end up with 1.5. Then I'll end up with 2. Then I'll end up with 2.5. And then I end up with 3. So actually, Peyton, I need 4 iterates, okay? Because I'm starting at y at 1, and I need to find y at 1.5, y at 2, y at 2.5, and then y at 3. So the way I would do my chart now is just that. Okay. So here's n, here's x, and here's y. When n is equal to 0, x is 1 and y is 1. I know I need to go 1.5, 2, 2.5, 3. So that's my 4 steps. So I'm going to need to compute. I already know this is y0. So I need to compute y1, y2, y3, and y4. And when I'm done, y4 is going to be my estimate for y at 3. Okay, so that's how I made my chart. So now, in order to find y at 1, what do we need? We need our function value f at xy. So what is f of xy if we go back to the form that we were solving? Anyone? What's f of xy? Okay, I give you a hint. Remember, the standard form of the differential equations we're solving is dy dx is equal to f of xy. And the problem I gave you is dy dx is equal to x times y. So that says that f of xy is just x times y. Okay, so if you remember our formula, y at n is y at n minus 1 plus h times f of xy. So that's going to be, oh, actually, let me replace that. That is f at x n minus 1, y n minus 1. So therefore, we're going to get yn is yn minus 1 plus h. And for us, we're going to get xn minus 1 times yn minus 1. And actually, for this one, we can make our lives easy. We could say that yn, we can factor out yn minus 1, and that'll give us 1 plus h times xn minus 1. So therefore, our approximation at x1, so x1 is 1.5. So we already know that x0 is 1 and y0 is 1. Okay, now we know that x1 is 1.5. So y1 is going to be y0 times 1 plus h. H is 0.5 times x0. So that is how we will find y1. Okay. So for us, we're going to get y1. That's going to turn out to be y0. Well, that's 1. Y0 is 1 times 1 plus 0.5 times x0, which is 1. So that's 1.5. Okay, so now we know y1, and we can go back up into the here, and y1 is 1.5. Okay. So x2 is 2. So y2 is going to be y1 times 1 plus 0.5 times x1. And so y1 is 1.5 times 1 plus 0.5 times x1, and x1 is 1.5. And that is equal to 2.625. So now we know x2. And then you can find y3 and y4. Okay, any questions about this and how I made my chart and how I was able to figure out how far I needed to go and how many iterations that I needed to compute? Any questions? Okay. All right, so what we're going to learn today is actually how to solve the ordinary differential equation. And so our first thing is our learning objectives. We're going to use the technique of separation of variables to solve a differential equation, and we're going to solve some applications using separation of variables. So I just want to remind you of the definition that I used on Tuesday, that an ordinary differential equation is an equation containing an independent variable x or t and a combination of a dependent variable y and its derivatives. And we said that a first order differential equation only has one derivative of y. So here we are looking at dy dx is equal to f of xy. Sometimes they will give you some initial information. Sometimes you will just get a general solution. Okay, so this is where we are starting today. We are starting with solving a differential equation that is dy dx equal to f of xy, where y of x naught is equal to y naught. All righty. So now the special type that we're going to be doing is a separable differential equation. All right, so the reason why it is called separable is because I can split f into a function of x times a function of y, or f of xy may be a function of x over a function of y, or f of xy may be a function of y over a function of x. Either way, I can separate it. Okay, so they are completely separate functions from each other. All right. So for example, f of xy what we just did equal to xy is separable. So I can let f of x, capital F of x, be x, and capital G, oh, I forgot to write the x. capital F of X can equal X and capital G of Y can be Y. But if I try to, let's say, take maybe the tangent or the sine of that, it will not be separable. So if I have F of X, Y maybe equals the sine of X times Y, this function is not separable. So I cannot make it just one function of X times a function of Y or a quotient. I can't do that. Okay. All right, so we're going to use the theory of differentials. All right, so how are we going to use the theory of differentials? Well, let me show you in the first example. So this first example is dy dx that says the derivative is actually equal to y. And we will see this in some population growth problems, temperature problems. So here, for example, we are saying that the rate of change of y with respect to x is actually equal to what y is at the current state. Okay. And I've given you an initial condition. So the first thing we're going to do is solve the general problem, and then we'll solve the specific problem. Okay, so the fact that this thing is separable, here you can see that f of x, y, f of x is simply just 1, and g of y is just y. So what I want to do is I want all the y's on one side and the x's on another side. Okay, so I'm going to divide by y. So I'm going to have dy divided by y, and then I'm going to multiply by dx. So I am actually using the differential dy and dx. So those are my differentials. Okay, now I'm going to integrate both sides. So I'm going to get the integral of dy over y is the integral of dx. Now, what is the integral of dy over y? We've seen this several times. This is something that comes up in many of our problems. What is the integral of dy over y? What is the integral of du over u?
Will be
Mikhail.
D.
Oh, go ahead, Caesar. I'm sorry. I'll let you
Yeah.
go.
Sorry, I'm just trying to remember kind of frankly. Is it the natural log of the absolute value of u?
It is. Thank you. Okay, so that means that's what I get over here. I get the natural log of the absolute value of y, but I'm going to get a constant, and I'm going to call that constant C1, only because when I integrate the other side, which is x, I'm going to get another constant from that, which I'm going to call C2. So now I'm going to make life easy. I realize that I get a constant on both sides anytime I do this. So since I know I'm going to get a constant on both sides, I'm just going to call that whole constant C. Because, oh, that should be C1. We get a constant on both sides when we integrate, so we can just actually throw it as one constant on the other side. So I get the log of the absolute value of y is equal to x plus a constant. Now we're trying to solve for y, and in some problems we won't be able to, but in this one we can. All right, we can absolutely solve for y. So if I take and I do e to the natural log of the absolute value of y, I will get e to x plus c. And I can write that as on the left-hand side, I just get the absolute value of y, which I'm going to be able to drop in a minute. And then on this side, I get e to the x times e to the c. And I notice that e to the c is simply another constant. So we have another constant here. So I'm going to call that a. So I get the absolute value of y is equal to a e to the x. And here I let a be e to the c, which was a constant. Okay, so now I know that if the e to the x is always positive, and the absolute value of y is a positive quantity. So unless my initial condition is going to make my y negative, which it will not, I'm able to drop this and just get y is equal to a e to the x. So this is my general solution. So this is the general solution. It's general because we still have a constant in it. So this is the general solution of the ODE. So here we have the general solution. All righty. So if the problem does not have a special condition like y of log 2 is equal to 4, then we would stop here. We wouldn't be able to solve for the constant. All right, but since we are given that y of the natural log of 2 is equal to 4, we need to use that to solve for a. All right, so we must solve for any constants. And in our case, our constant is a. So now we're going to let x, so here, x is equal to the natural log of 2, and y is equal to 4. So we're going to put 4 in for y. We still have a, and we're going to have e, and we're going to have the natural log of 2. So how do I solve for a? We need to use some of our properties of exponentials. Do you guys remember those properties of exponentials? Can we simplify e to the natural log of 2?
Wouldn't that be just 2?
It is just 2. Thank you. So now I get 4 is equal to a times 2. So that implies a is 2. All right, so now we're going to get a unique solution, and our unique solution is a is 2. So y equal to 2e to the x. I go back and in the place of a, I put 2. All right, and this is our unique solution. Okay, so now we have a unique solution to our differential equation. Any questions? All right, so when we go back, remember, let's think about this. Remember we said the only function whose derivative is equal to itself is an exponential. So we started out with dy dx, that's derivative equal to the function itself. And what did we get? That y has to be the exponential e to the x. Okay. Any question about that first example? Okay, here is our next example. And I do realize that I forgot a condition. So let me put my condition in here. My condition is y has to be bigger than -1. Uh-oh. That always, yeah, y has to be bigger. Uh-oh, wrong place. The -1. I don't know why it does that. That is so strange to me. Let me put the -1 in and then go back and put the point in, because that little symbol means something different than, there we go. Okay. All right. So we're going to do the same thing here. As you can see, somebody tell me what the function of x is. What is the function of x? F of x is equal to what?
Is it 1 plus y?
Okay, so think about what you just said. Does 1 plus y have x's in it? I think that's g of y. So 1 plus y is the function of y. Okay, so now we've got the function of y down. So what's the function of x? It's the only thing left.
E to the x?
Right, okay. So Peyton, g of y can only have y's in it. And f of x can only have x's in it. They are separable, okay?
Okay.
All right. Okay, so now we're going to do the same thing. I'm going to put all the y's on one side, all the x's on the other side. So I'm going to take dy, and I'm going to divide that by 1 plus y. And I'm going to take e to the x and multiply that by dx. Okay. So now I am going to integrate. So I have dy over 1 plus y. And I have e to the x dx. Okay. So this is similar to the last one. We're going to get the log of the absolute value of 1 plus y. And this side, we're going to get e to the x. And as I said, we can throw the constant on one side. It really doesn't matter which side we throw it to, but that's where I decided to put it. And so notice that right now, if we solve for y, we would have e to the 1 plus y, but then we're going to have e to the x. And that kind of can give you a headache. So we're going to leave it in this form, and this is an implicit form. of the solution, of the general solution. So implicit meaning I don't specifically have y equals. So that's the implicit form of the general solution. That one was quite easy to get. Okay. And then I thought I put a initial condition on that. Oh, I did. Here it is. Y at 0 is 0. I thought I got an initial condition. Okay. So let's put in y. So when x is 0, y is 0. So we're going to get the log of the absolute value of 1 plus 0 is going to equal e to the 0 plus c. So I get the log of 1 is equal to 1 plus c, but that says 0 is equal to 1 plus c. So c is -1. So now I'm going to get the unique solution, the log of the absolute value of 1 plus y, which we don't even really need anymore because we know y is greater than -1. So I can put that in parentheses. Is equal to e to the x minus 1. And so this is the unique solution. Okay, any questions? You guys seem to be rolling right along. Okay, so this is number 3. And I want you guys to set it up with the differentials and the integrals while I take roll. Okay, anybody want to tell me what they have as in terms of 2 integrals?
I have dy, I'm sorry, the integral of dy over 2x equals the integral of root 1 minus y squared dx.
Okay, so let's think about this. What's f of x?
Would that be the square root of 1 minus y squared?
Okay, so f of x can only have x's in it.
So then it's 2x.
2x, okay, good.
Oh, okay.
And what's g of y?
Now that should be the root 1 minus y squared.
Okay, now remember, the y's are going with the y and the x's are staying where they are. So the y's move to the left and the x's stay where they are except for the dx, which moves up to the left, to the right. So can you, now that you have a little bit more information, do you think you can try it again?
Yeah, so that would be the integral of dy over the square root of 1 minus y squared,
Okay,
which equals to the integral of 2x dx.
thank you. All right, excellent. Okay, everybody see that? Okay, so we split it up and making use of differentials. We move all the x's to the right and we move all the y's to the left. Okay, All right, so now it's time to integrate. How do we integrate the left-hand side? It is a known integral. I even give you more of a hint. It is an inverse trig function.
Arc sine.
Okay, so who's talking?
Victor.
Hi, Victor. Okay, so what did you get? So you got the sine inverse?
Sine inverse of oh, what's it supposed to be the constant over
It is. You are so right. It is y over the constant. But what's our constant in this problem?
1.
Good. Okay. Then what's on the right-hand side?
Oh, sorry. It'll be 2x squared over 2.
Okay. So that just gives me x squared.
Or sorry, x squared over 2.
Okay, and a constant. Okay, any questions about that? All right, so we have the sine inverse of y is equal to x squared plus a constant. All right, so one of the things I can do is I can plow through and take the sine. So the sine of the sine inverse of y is equal to the sine of x squared plus a constant. So that gives me y is equal to the sine of x squared plus c. All right, so that is my general solution. I have not solved for the constant. That's my general solution. Now, I did give you some information. If you look, when x is 0, y is 1 over the square root of 2. So that says 1 over the square root of 2 is equal to the sine of 0 plus c. So that is the sine of c. So the sine of c is equal to 1 over the square root of 2. Now that could be a whole lot of values, can't it? All right, because that can be, c could be pi over 4. C could be 3 pi over 4. So how do we know which one to choose? Well, if we go back to this part of the problem where we had the sine inverse. So right here, we had the sine inverse of y. So if we take the sine inverse of 1 over the root of 2, that gives us pi over 4. So the sine inverse from before of 1 over the root of 2, that gives us pi over 4, because the sine inverse function only gives you values between negative pi over 2 and pi over 2. So now we know c has to be the pi over 4 value. So we get y is equal to the sine of x squared plus pi over 4. Okay. Any questions? All righty, one more, and I'm going to let you guys do this one. All right, how do we handle this one? All right, so this one is actually written in a different form. So if we look at this one says y times x plus 1. Y prime is dy dx. And that is equal to x times y squared plus 1. So notice the functions of y are here and here. And the functions of x are here and here. And now that I think about it, I don't think we can actually use this initial condition. So I'm going to delete it, and we're just going to have a general solution. Okay. All right. So anybody have an idea of what it's going to look like with y's on one side and x's on the other?
Would it be x over x plus 1 and then y over y squared plus 1?
Okay, so on this side, I'm going to get y over y squared plus 1 dy. And on this side, I'm going to get x over x plus 1 dx. Okay, any questions? So now I have y's on the left and x's on the right. Even though it wasn't given to me in the specific form, I was able to put it in that form. Okay, now we have to integrate. Okay, so now we're going to integrate this side and we're going to integrate that side. All right, so let's look at the left-hand side. The left-hand side is the integral of y over y squared plus 1. How do I integrate that? How do I integrate this problem? Chara? Chara,
Yes.
how do I integrate this? I give you a hint. It's not difficult. It doesn't involve
I
any.
can't remember right now.
Okay, so let me help you. Do you see a function where I could actually make it do a u substitution and its derivative or some form of the derivative is nearby? So I want to do a u substitution for this. Okay, that doesn't jar your memory. Why don't I let you be y squared plus 1? Okay, Chara, what's du?
2y.
Oh, you stopped.
Is it not 2y?
Okay, 2y dy. Don't forget that, remember? Okay, because in this problem, we have y dy at the top, right? You see y dy?
Yeah.
I have to solve for that. So what's y dy?
du over 2.
du over 2. Thank you very much. Okay, so now this integral looks like du over 2 divided by u. So that is 1/2 the integral of du over u. Well, we saw this a minute ago. That's 1/2 the log of the absolute value of u. And then I'm going to get a constant. So this is 1/2 the log of the absolute value of y squared plus 1, which we already know is positive. So I can just do y squared plus 1 plus a constant. So that's the left-hand side. LHS, left-hand side. Okay. Now we need to do the right-hand side. And that's the integral of x over x plus 1 dx. Now, this is one we just learned in the last module. Okay, this is one we just learned. This is a case we're integrating a rational function, and the power of the numerator and the power of the denominator are the same. So what do we have to do for this one? Power of the numerator and the power of the denominator are the same.
Would you subtract the powers if you wanted to do it in division 1?
Okay, so we do have to do the long division. That is correct. So we're going to take x plus 1 and we're going to divide it into x. So x plus 1, so x goes into x 1 time, and 1 times x plus 1 becomes x plus 1. And then when you subtract, x minus x gives you nothing, and this is a 0 here. So 0 minus 1 gives you -1. So we find out that when we integrate x over x plus 1, that is the same as integrating, well, we get 1 minus a remainder of 1 over x plus 1. Okay, so that's what we get. And when you integrate that, we get x minus the natural log of the absolute value of x plus 1 plus a constant. Okay, so I now have my left-hand side solution, which is 1/2 the log of y squared plus 1. So I get 1/2 the natural log of y squared plus 1 has to equal the right-hand side, x minus the natural log of the absolute value of x plus 1. And remember, we put the constant on one side and we are done. We have a general solution. Okay, any questions? So that one was a little bit more work. It required us to have to figure out how to integrate the left side and the right side. Okay, so we started off with something that didn't look familiar, but we knew y prime was dy dx. Then we separate it. Then we integrate the individual pieces, the left side, which is the y problem, the right side, which is the x problem, and then we're able to put it together. Okay, any questions? Okay, there are going to be some problems that don't look like they're separable. So for example, you might see something that looks like dy dx is e to the x plus y. Now that does not look separable, but it is, because this is dy dx is e to the x times e to the y. And so therefore you put the e to the y on the left-hand side. So you get e to the negative y dy is equal to e to the x dx. And then you continue with the problem. Okay, so it may not look separable, but sometimes you're going to have to use properties of logs, exponentials, and other things to make sure it is separable. Okay, any questions? Okay, so this turns out to be negative e to the negative y is equal to e to the x plus a constant. So we could write this as e to the x. Oh, well, basically I could leave it like that. Or I could solve for y, but we're going to leave it like that because y is in the exponent. So I would write this as e to the x plus e to the negative y is equal to a constant. And this is just an implicit solution. Okay. All righty. So we have some applications of this. All right. So the first application is Newton's law of cooling. And I like this application. Give you a chance to write this down. So this is the first application. Newton's law of cooling. So T is the temperature of an object. Okay, so it could be the temperature of a ball, let's say, or an ice cube. And T sub S is the temperature of the surrounding medium. So maybe we're taking this ice cube and we are putting it into something hot. And then T naught is the initial temperature of the object. All right, so we're going to use all of these, T naught being what T up, basically T at when T time is equal to 0 or whenever you're starting your calculation. Okay, so what does Newton's law of cooling say? All righty, so Newton's law of cooling says the rate of change of the temperature of an object is proportional to the difference in the temperature of the object and its surrounding medium. Okay, so of course we all know, maybe we don't, but temperature always, heat always flows from which direction? Hot to cold or cold to hot? If you go outside and it's 10 degrees outside, what happens to your body? It starts to lose heat because heat flows from hot to cold. Okay, if you go outside and it's 110 degrees, you start to sweat and warm up because all of that heat is trying to jump into your body. Okay, so the change, here's the rate of change of temperature, T. with respect to time. So that's how temperature is changing over time. It is proportional, okay, proportional to the difference between the temperature of the object and the temperature of the surrounding medium. Okay, so that's what that means. Okay, so we can rewrite that. If something is proportional, that means it equals to a constant times the item. So we get that the derivative of temperature with respect to time is actually equal to negative K times T minus TS. And here, K is the diffusivity of heat. And all objects have a different K. A steel ball is going to have a different K than an aluminum ball or a copper ball. They all have their own diffusivities of heat. Okay. And the assumption is that K is positive. All right. So if the temperature is greater than the surrounding medium, so if T is greater than TS, this will be positive. K is positive. This is negative, which means if the temperature of the object is greater than the surrounding medium, the change in temperature of the object decreases. In other words, it starts to lose heat. Okay. If the temperature of the surrounding medium is smaller, so my temperature is less than outside, then K is still positive, and this is negative, which means my temperature is going to start to increase. Okay, so this is the right formula for us. And we are given an initial amount of information, initial condition, that is T at some time 0 is initial temperature T naught. Okay, so just like I said here, T is the temperature of the object, T sub S is the temperature of the surrounding medium, and T naught is the temperature of the initial temperature of the object. Okay, any questions so far? All right, so let's solve this problem using separation of variables. So this time, our dependent variable is capital T. And our independent variable is little t, which is time. So now we're going to get all the capital T's on one side and all the little t's on the other. So I'm going to get D capital T, and then I'm going to divide by T minus TS. And I'm going to keep the negative K on this side, and I'm going to multiply by little dt. All right, you guys with me? You want to type in the chat, please type in the chat. If you don't know what's going on or you're lost, please type in the chat.
I have a question.
Oh, yay, we're talking. Yay, Peyton, what is it? I'm so excited.
Yeah, this one, is this something new or is it related to what we just did?
Oh, this is exactly what we just did. Okay, that is a wonderful, phenomenal question. So let's go back. This is an application. So let's go back. So in these problems up here, I'm gonna go back specifically to maybe this one. In these problems back here, we had Y was the dependent variable and X was the independent variable because Y was a function of X. And it was separable because it only contained X's and Y's. And we put all the Y's on one side and all the X's on the other side. Okay, so this is the same, except now we're using T's and capital T's and little t's. Okay, so we use capital T, that's basically like our Y, and little t is like our X. So that's why capital T is the dependent variable and little t is our independent variable. So now, instead of what we had before, where we had dy dt, dy dx equaled a function of x times a function of y. Now we have d capital T, d little t is equal to a function of little t and another function of capital T. Okay. Peyton, does that kind of help a little bit?
I'll be honest, no, but you know how I am. I spend the office hours and then I understand.
So I know sometimes it's hard when we switch variables. Why don't we do this? Why don't we do this before we do the temperature problem? Why don't we do the radioactive decay problem? Okay, so I'm going to switch out the temperature problem for the radioactive decay problem first, only because some of you, I know Peyton is having an issue. So let's adjust the lecture. So I'm gonna adjust the lecture just a little bit and do the radioactive decay problem first. Okay. So the radioactive decay problem uses Y's and T's. So maybe that might help just a wee bit. All right, so I'm going to simply adjust what I was doing and do it in a different order. Okay. All right, so we'll get to the temperature next time. We're going to do radioactive decay. So clear our brains for a moment. Forget about temperature. We're going to do radioactive elements. So when atoms are unstable, they spontaneously emit radiation by a process called radioactive decay. So we can, same thing with carbon dating. Something has a certain amount of carbon in it, and then over the years, the carbon will decrease out of the element, out of the object. And that's how they can tell basically how old bones are, because they can look at the amount of carbon that's still left in it, so they can do carbon dating. So same thing with radioactive decay. All right, so the rate of decay is proportional to the amount present. So it's very similar to the temperature problem I was going to do, where I said the temperature is proportional, change in temperature is proportional to the temperature present. Well, here the rate of decay is proportional to the amount of radioactive decay, amount of material present. So dy dt is proportional to y. So instead, I'm going to get dy dt is equal to minus ky. So I'm going to get this problem here. All right, so this one is very similar to the other one that we did. I wanted to do this one last because this one involves half-life and some other difficult stuff, but we're going to make our way through. Okay, so if it's proportional, that means it's equal to a constant times that thing. And since it's decaying, we want the rate of change to be negative so that the function will decrease. Calculus 1. When the rate of change of a function is negative, it's a decreasing function. So that means y will be a decreasing function. So here we're assuming k is positive. Okay, so this is radioactive decay. Now we can solve this. All right, so how do we solve this? we get same way. So now we're going to have dy over y is equal to negative k. And this time our independent variable is t. So instead of having x's and y's, we're going to have t's and y's. And I know you're saying, why do we have to change the variables? Because different problems, if it's a time, we use t. If it's temperature, we use capital T. If it's a population, sometimes we'll use capital P. If it's an amount of money in the bank, we may use A. So we use different variables. Okay, we already know that when we integrate this, we get the integral of negative k dt. So this gives us the natural log of the absolute value of y is equal to minus k times t plus a constant. Now, I know that we're looking at the amount of a material, so y is positive. So this is just the natural log of y is equal to negative k t plus a constant. Okay, so when I do e to that, so I do e to the natural log of y, I get e to the negative k t plus a constant. But remember, I can split that to e to the negative kt times e to the c, and we made that e to the c equal to an a. So I get y is equal to a e to the negative k t. All right, so this is what we're using to describe our radioactive decay. And let's see, what do I want to use with this? Oh, here it is. Okay, so we're going to assume that y is equal to some initial amount when t is equal to 0. So we don't, right now, we don't know what that initial amount is, but we do know that if we put in t is equal to 0, we get y naught. So we get y naught is equal to a e to the 0. So that says a is y naught. So now we get an formula y of t is y naught e to the negative k times t. So this is the solution to the amount of material defined by radioactive decay. All right. Any questions? Peyton, is that a little bit better?
Just a little bit.
Just a wee bit? Just a wee bit? Okay. All right, so first question, find the half-life. Whoa, what does that mean? Okay, so when we want to find the half-life of material, that means we want to find what is the, at what time is half of the material present, or half the material has decayed and only half the material is left. So at what time t has 1/2 of the material decayed, or again 1/2 of the initial amount is left or present. Okay. So that's the half-life. All right, so here, this is how we find the half-life. So at that time t, so at the half-life, I want that to be black. Y of t will equal 1/2 y naught. That's 1/2 of what was initially present. So that says then that we want 1/2 of y naught to equal y naught e to the negative kt. So now, as you can see, we can divide y naught out of both sides, and we get 1/2 is equal to e to the negative kt. I can take the log of both sides. So the log of 1/2 is equal to the log of e to the negative kt. So what happens when I take the log of e to something?
It'll be the exponent itself.
Just get the exponent. So I get the log of 1/2 is equal to negative kt. So I get that t is equal to negative log of 1/2 divided by k. And I'm gonna leave it to you to figure this out by the log properties. This becomes the natural log of 2 over k. Okay. So that's the half-life. So this is the half-life. And we will pick up here on Monday. Any questions? Any questions?
Is there any office hours today? Or they're already-
Actually, there is. I'm having office hours at 3 today
Okay.
for anybody that wants to come.
And will these notes be posted on Blackboard?
Yes,
Okay, thank you.
you're welcome.